Hi, in this video, we want to take a look at exploratory multidimensional item response theory. Okay, so remember that when we start talking about item response theory, we're really talking about factor analysis simultaneously. So that the factors are like the predictors in our item response theory model. All right, so far in the videos that I've created, all of the item response theory models have one factor as predictor. Now we want to expand upon that. We want to have more than one. So in this example, we're going to look at two factors, and hopefully the audience will be able to generalize that to 3, 4, 5, whatever is appropriate. Now, because of the nature of factor analysis, we're not going to want a lot of factors. If I have 10, let's say, questions on a test, potentially I could have 10 factors going on. But also simultaneously think about factors in terms of like a dimension reduction aspect, because there is a connection with principal component analysis. And so we want to keep the number of factors relatively small. Now, the more questions I have, the more factors I could have, but always just kind of lean towards being lean on your number of factors whenever you do a multi-dimensional item response theory model. All right, the example for this video is coming from Modern Psychometrics with R. It's a Springer book, and here is the website on GitHub to get the code that I modified. All right, so what we're going to do, we're going to extend one factor item response theory to 2 or more factors. So let's go ahead and get our data. So from the MPsycho R package, that is the books R package, we're going to get the Zariski data set. Okay. And we're going to limit things to the actual items, the actual questions that are associated with that. So this one is an addition and subtraction test. So these 16 questions are part of that test. Now there are other columns in the data set, but those are covariates that are not items, so we don't want to keep that in there. All right, so now let's go ahead and explore the number of factors. So what we're going to do, we're going to run print cows, since this is not, so the data is I think it's binary or ordinal. It does, I can't recall. It doesn't really matter for us conceptually for this example. But what we're going to do, we're going to run the Giphy package print cows, and we're just going to get the print cows out. And now let's go ahead and plot it, just so we get a feel for what's going on. And so here I'm going to do a loadings plot. So what's going on is that the arrow tells us the first factor and the second factor simultaneously. So if I look left to right along the x-axis, that's the value for the loading on the first factor, and the vertical in the y-axis direction is the loading of the second factor. Okay, so when we look at this, we see that all of the arrows are pointed to the right. And, you know, since this is a math test, we're going, you know, being stronger at addition would probably be stronger at subtraction, right? Addition and subtraction would not be separate components mathematically. So, you know, like how, let's say, you know, German literature would be completely separate from Snell biology. If we gave people tests on those two subjects, those would be very separate from each other conceptually, but these are these are directly related. And so since they're all pointed in the same direction for the first component, I conclude that the first factor is evaluating their overall ability on these topics. Okay, so what is the second factor? Now this one's a little bit trickier. So look at the major ones up here and the major ones down here. What the second factor is, or second component is measuring, is the contrast between their mastery on these two. So this axis measures their overall ability. This axis measures, are they better on one part of the test than on the other? And it's basically grouping the test into 2 types of questions. And the vertical position for component 2 tells us where are they better, you know, considering their overall ability. Now we can also take each, so I'm expanding upon the biplot a little bit, and I'm taking each individual subject's component values, and I'm plotting them. So the people who are farther to the right are those who have the stronger overall mathematics ability, and the ones over here on the left are going to have the weaker overall mathematics ability. Now, if I could look at, let's see, this subject here and this subject 251, they have about the same overall ability, but you can see that the questions that are like upward, this student is better at the ones that are pointed upward than the ones that are pointed downward. This student is better at the problems that are pointed downward more than the ones that are pointed upward. All right, so even though these two students have about the same overall ability, we see that they have different focuses in their actual abilities and their shortcomings. All right, so this student, if I wanted to get the student more proficient overall, I would work with them on the ones that are pointed downward. This student, if I wanted them to get more proficient overall, I would work on the ones that are pointed upward because that's where they're weak. Now, a student that is over here, what we could do is take the ones that have the longer pointed to the right, the greater X value to the right, because those are the ones with the least amount of effort, we get the greatest gains on overall ability. So this is something that's very nice. For each individual student, we can look and we can diagnose where they're at, and we can figure out how to help them very quickly. So we've got like two ways to look at it. First component, if I go with the ones that have larger to the right values, then that's going to help their overall ability more. If I'm going with the ones that point up or down more when I'm working with a student, then I have the option of working where they're weakest so we can get the quickest gains for them. All right, so now let's take a look at the discrete plot. So when I look at the discrete plot, I can see that one is definitely going to be the highest. And then the second one, we have a big drop. And then things get pretty flat. And so remember, when I look at discrete plots, there's two rules of thumb. One is that I want greater than 1. Another one is I want where there's an elbow. Okay, so this is where there's an elbow. So this is saying that we should go with 2. The other criteria is to go above 1. Now, I don't like the above 1 criteria because eigenvalues are dependent on the scale of the values. If I just rescale a column, I could end up getting bigger eigenvalues or smaller. So I don't like that one, but you could use it, and you would see that you would get maybe 5 factors. But realize that if you were to go with 5, you really haven't picked up a lot more than just having 2. And that's displayed by the fact that this is so flat. Now, another criteria that we would choose for using the number of factors is we want to have our cumulative variance to be above a certain threshold. And their idea threshold to be able to do it. And the cumulative variance will be the sum of consecutive eigenvalues. All right, so now let's go ahead and let's build a one-factor item response model. All right, so I'm going to use the MERT package, the MERT function. So it's MERT. I pass the data. Remember, so this is all the math questions from the test. I dropped all the covariates. Here I'm saying I only want 1 factor, and here this tells us the model structure. And I put verbose equals false because there's going to be a lot of iterations to be showing. My dog is putting her nose up against me. She's so sweet. She wants some attention. I'll play with her after the video. All right. Okay, so this is a typo. That should be a 2. I put down a 1. I apologize. All right, so I'm doing the same thing, except for now I have a 2-factor model. Okay. And now I want to compare the models. All right, so when I do this, I'm going to run ANOVA. I have object 1 and object 2. Remember, whenever we run ANOVA, we're always comparing 2 models. Even if I only pass 1, then it's, if I only pass 1 model, it's comparing it to the constant model. Here, since I've got 2 models, it's comparing the 2. Okay, and here we can see the p-value is very small. So we conclude that there is an informative there's a difference in the informative value of the two models. Okay, well, that leads me to believe that the two-factor model is better than the one-factor model. All right, so let's go ahead and take a look at some of the statistics. So our AIC is just about the same. There's a little bit of a difference, but not much. And here is a modified version of BIC. Here is BIC. So there's a little bit of a lot. So AIC says the second model is better, but then the modified AIC says first one's better, then first one's better. First one is better, then first one's better. Now here, this one is less negative. So if I don't consider the additional terms on there, the log likelihood indicates that it's a better model. And since we conclude that the second model is better, let's go ahead and look at some statistics on that a little bit further. So here is the root mean squared error average. Here we've got a confidence interval on that. All right. Let's look at the item fit statistics. And you'll notice that I went ahead and I sorted everything by the p-value. That way I can look to see, I can conclude, I can try and find where do I have a lack of fit. And that's going to be with the smaller p-values. So I'm concerned about these right there for a lack of fit. But overall, that's only 2 out of several items that's involved. I'm not too worried about it. Remember, if I keep on doing lots and lots of hypothesis testing, I'm going to end up having things that look statistically significant just off of random chance. Maybe not random chance, but that's our model. That's how we model it. All right, so let's look at different rotations. So remember that different rotations will give us different values, and usually it doesn't make it, morally speaking, things say the same, but there are nuanced differences. The rotations are why if I do one component and then I do 2 components, the first one here does not necessarily match the one over here. If I do strictly principal component analysis, the first one here and the first one here will always match up to a sign difference. All right, so here we can see the factor loadings under Varimax. Trying to maximize the variance. Here we can see the factor correlations, which means they're orthogonal. Here we have oblique minimum. And here we have our factors, loadings. And we see that here under this rotation, we do not have orthogonal factors. And we have a negative 0.5 correlation. Okay, so now let's go ahead and visualize the two-factor model. So I've got 2 factors and I have a likelihood. So I could do a logistic regression curve, a logic curve to visualize it. And so this is going to be a 3-dimensional plot. So I have the first factor along this axis, the second factor along this one, and then I have the probability of getting added 3 correct off of this. And so we can see that as we go along this direction, where as factor 2 becomes more negative and factor 1 becomes more positive, that's where we get the steepest ascent on the probabilities. So I can tell you off of this picture that added 3 is in the negative direction on that biplot that we did. Now we can get our multidimensional difficulty index. Now this is a little bit more complicated than in terms of interpretation. This is more difficult than what we had for 1-factor models, because there's no matrix algebra stuff going on. There's a little bit that we have to do to get this to be interpretable as a difficulty, to take the parameters and work it out. But conceptually, we can just kind of loosely think of it as difficulty index, even though it's not quite right. The textbook goes over the difference. Now we can plot the individual estimated factor values. Now something I did in this plot, what I did was I took the class, which is a covariate, and I colored each of the points by the class. Okay, so class is a covariate. It's got 3 different levels, and you can see I plotted it. So 1 is black, 2 is red, and 3 is green. Okay, so we can see that the black kind of like takes up the whole range, and there's a region over here that's mostly black. We can see that the red and the green overlap in their regions pretty closely. Now, if you think you see a trend in something like this, to test it, a good rule of thumb is to take 1 point and move it. If you can move any point and come up with a different interpretation of this plot, then your visualization, your interpretation of the plot is wrong. So that's a good way to go. So when I look at this, I was starting to think that red and green had different regions, but if I was to put a red dot right there, if I put this one up and put the red there, I would see them as being the same over here and similar elsewhere. So I think red and green are pretty much overlapping in the same region. Black is a little bit different, basically just because of up here. All right, so now let's compute the differential item functioning statistics. So remember, differential item functioning is just concerned strictly with bias. And so we're trying to see, is there bias in these questions? All right, so here, what we're going to do, we're going to group all those red and those green points together. We're going to take the third, fourth, and the third. Oh, so sorry, we're going to take the third graders and the fourth graders and put them into one group, and we're going to have the second graders. So second graders are those black dots, third graders are the red, and the fourth graders are the green. We're putting third and fourth into one bin, and we're going to want to do some hypothesis testing. So here our group is class 2, which was defined up here after we did our binning. And now we're going to run some hypothesis testing. And here we're going to make sure that we are adjusting our p-values for false discovery rates to protect ourselves from inflating the type 1 error risk. And here I get my p-values. So we see that even after making the p-value adjustment, we have a lot of them that are statistically significant. So we have here, that looks like a lot of the subtraction, it's a mixture. We have subtraction and addition on these. And the added 7 is really close. So what I would do if I was the person that was writing this test, I would want to review those questions so that I get feedback on biased question writing to make sure that I can do a better job next time. Also, if I was going to use that question again, I might want to reevaluate it, either edit it so that there doesn't appear to be a bias in it. I might have to change the curriculum for the students to make sure that we don't have bias in our curriculum, or I might want to just throw the question out altogether. All right, well, that's all I've got for you. Take care and goodbye.